Hey, welcome back. What we will be discussing in this lecture is the idea of a priority queue. The priority queue is going to be one of 4 restricted ADTs that we look at this semester. By restricted, I mean, we have some sort of limitation on them in some way. For example, the stack and queue were the first 2 we looked at, and the list ADT was pretty well open. You could add what you wanted. You had your insert, remove, and lookup. And we had the same thing for a tree and the various tree structures we looked at. Where for stacks and queues, they tended to be more limited, and there was a sort of a standard limited set of operations that we said are standard to the ADT, and you tend not to have other operations other than that. Priority queues will be the same way. They'll be a little more relaxed than stack and queue, but there will be a focus on a certain core set of operations, which are going to be insert, which is the parallel to push or on queue. We will have delete min, which is the parallel to pop or day queue. We have the operation find min, which is the parallel to front or top. And then we have is empty, just like we did for stacks and queues. So we have 4 core operations, just like we did for stacks and queues. When we talked about a stack or a queue, we had a linear structure. There was a definite first and second and third and fourth element. And so the question was, well, we're inserting on one end of this linear structure, and we're removing from some end of this linear structure. And with stacks, they were the same, and then with queues, they were different end. Now, as far as priority queues, we're dealing with just a set. So instead of having a linear structure to these elements and saying there's a first element, there's a second, there's a third, the idea is here, this is, as we've been looking at already, just a set implementation. And so basically, we don't have a first or a second or a third element. We just have a collection of elements. And so when we deal with inserting into the structure, we don't need to have something like on queue or push where we're putting it somewhere. We're basically, as far as a conceptual idea anyway, we're just taking a new value and going ahead and throwing it into the collection. There's no place to put it because our conceptual view is not that we have a linear layout of elements that we're now removing from an end and inserting on an end. Our conceptual picture is just a bunch of elements. And so there's no particular ordering to them that we know of conceptually. Of course, behind the scenes in a data structure holding these conceptual elements, there likely is some sort of a structure that we may or may not use. But conceptually, we just have a set of elements. And so insert just says toss an element into that set. Likewise, delete min will remove an element from that set, specifically the minimum element. So in order to use a priority queue, you have to have less than defined on your structure. And so in this case, if we were to do a delete min, we would be getting rid of A, because that's the lowest of these characters in alphabetical order. Likewise, if you have numbers, you remove the lowest number, and so on. And then you have the idea of find min, which just returns without removing, just like we did for stacks and queues. And then is empty will tell you if the set is empty or not, the priority queue is empty or not. And so that way you know whether it's safe to do a delete min and a find min or not. So there's a parallel between stacks and queues and priority queues. What we're essentially doing here is dumping things into a set and pulling them out in lexicographical order. Numerical order, alphabetical order, whatever the order happens to be. And so there is, in fact, a sorting algorithm based on this called heap sort, which basically says take a bunch of elements, insert them into a priority queue one by one, and then remove them one by one, and you remove them in sorted order. And I've just described a sorting algorithm to you. So it's a really nice structure to use in that regard, and we're going to be looking at implementations for it in a moment. As far as what we might add to this ADT, unlike with stacks and queues where we said, okay, it's even odd to add, facilities to read other elements besides the top element or the front element, and certainly we tend not to add facilities to write into the middle of the structure. Priority queues, we can add other facilities. We'll have those 4 operations. You might add, as you'll see in Adam's section tape, you might add ability to increase or decrease a particular value in the priority queue. You might have a general search and remove, which looks for something and pulls it out of the set. And so you may have a number of other operations you might add to this. However, these are the core operations, the ones we worry about most, and the implementation choice will be optimized for those 4 operations. So if you say, well, I want to add in, the ability to, remove, search and remove something, and I want that to be as fast as possible, you're not really so much dealing with priority queue then, though it may, have the duplication of the features. But generally, when we talk about a priority queue, we're talking about an ADT where these are the most important operations to us. Whatever else we might choose to add in is up to us, but we're concerned about optimizing the implementation so that those 4 operations run as quickly as they can. And then anything else that gets added on is generally added on to that implementation. As you know, certainly you're always ultimately free to do whatever you want, but when we talk about priority queues and in general when they're discussed, that's the idea behind them. And any deviation you take from that is sort of a variant of the standard data structure. So that's the idea behind the priority queue then. Conceptually, basically what it is think of a regular queue. What the idea of a queue was we had this broad collection of elements, and as we inserted, we'd be dumping into the collection. And then as we removed, we happen to be removing the first element that had been inserted, and then the second element that had been inserted. What we're doing here is we're taking a broad collection of elements, and what we're removing is the element with the top priority, the element with the second highest priority, and so on. So it's sort of like as if each of these is some sort of a priority mark. For example, a process scheduler on an operating system. You have a bunch of people, that all want to run their jobs at once, and some people have more priority than others. For example, a system administrator that needs to do run some program that will check certain things about the system, a maintenance program that checks and reports certain data or whatever, evaluates something wrong with the system. That might have a higher priority than a job, some standard MP that you or I are trying to run. So if everyone's got their jobs backed up waiting for the chance for processor time in a large time-sharing system, then certain people might submit jobs and get them moved up to the front of the line. It's as if you're at a bank. You can use the analogy for an original queue that we talked about already of a bank where a bunch of people are in line and they each take their turn at the bank window. And now you may have someone who maybe there's someone who's got a very high priority, a valued bank customer, or someone is sick and needs to get to the hospital and they have to stop the bank for some reason. I don't know, it was a bad example. But anyway, the idea would be there might be some people that might be let in line ahead of you with certain distance because of their higher priority for whatever reason. Or an elderly lady that can't stand for too long, people might let her ahead in line or whatever. So there's kind of a real world idea. When we're dealing with computers, you've got this processing scheduling concept, which is the same idea. And there's one example where a bunch of jobs are waiting for their time slice, but some people might actually get to move ahead in line even though they came to the line later than you did because of priority. And so that's really the conceptual difference between a priority queue and a regular queue. A regular queue, you've got a collection of elements that you remove in order of insertion, so you can sort of think of the queue as being a linear arrangement because the linear arrangement allows you to keep them collected in the order they were inserted. Where for a priority queue, they're instead removed not in the order they were inserted, but in the order of their priorities. So the question then is, well, what can we do as far as implementation goes? And, well, we've looked at a number of data structures so far already this semester that are capable of implementing that ADT. How do they compare to each other? And so let's consider, for example, a linked list, which is, probably this goes back to be the simplest example we can deal with here. And we can actually deal with 2 different versions, unsorted and a sorted linked list. So if we're going to deal with an unsorted linked list, well, you have the ability there to just dump values into the linked list wherever you want because it's unsorted. So if I want to insert a new value into the linked list, I have a linked list of integers and I insert a new value, put it wherever you want. You can even put it on the front, which would be very quick. So we could say that insert would be constant time. Question is, how do delete min, I'm just going to abbreviate here, how do delete min and find min work out on a linked list if it's unsorted? And the answer is, if you're trying to run a delete min or a find min on a linked list, if the linked list is not sorted, then your value could be anywhere. And so you would need to search the linked list for it. We've talked about searching on a linked list. We've got an additional problem in that we're not just looking for a specific value, we're looking for the minimum value. And in order to know the value is the minimum, you need to have looked at everything to know for sure that the value is the minimum. Which means what we have here is a situation where I need to look at every single cell in the list, and then once I've done that, I could have been keeping track of the lowest I've found so far. Once I look at that last cell, and at that point I would say, well, if this is the minimum, then the last cell is the minimum. Otherwise, whatever I've been keeping track of up to this point is the minimum. And the same thing with find minimum. Whether we're removing it or just looking for it, we have linear time for this process. Change the battery in the microphone. Hold on. Sorry about that. These batteries have a way of showing that they're getting low right in the middle of a lecture. So that said, so that's the issue that's going on there. Is, I mean, once you find it, it's easy enough to remove it because you've been, keeping track of your previous pointer as you've been traversing down the list the whole time. But knowing it's the minimum to begin with is an order n operation. On the other hand, for a sorted list, if you're going to do a delete min or find min, then your minimum is right in front rather than who knows where, and so that would be constant time. But your insertion, if you're going to insert a value, well, now you have to search the list to figure out where to insert it, and that's going to be constant or linear time in the worst case. Now, is empty I haven't written here because that's easy. If your list has no elements, then it's empty, so that's constant time no matter what. So dealing with this, then, we can say that, okay, if we've got an unsorted linked list, then insert's going to be constant time, and delete's linear, and if it's sorted, then delete and find min are linear, and are constant, and insert is linear. And what does this mean for us? Well, certainly we can't do more deletions than insertions. If I only put in 5 values in a priority queue, I can't delete 10. On the other hand, I could do more insertions than delete mins, so we might say this is the superior choice, because at least that way the operation, there's at least as many inserts as removals, and so if you plan to do a lot of delete mins, not too many find mins, then you might say, well, I'm going to try and optimize my insert. However, we don't even have a chance of an n over 2 average case here. This is, even in the best case, going to be linear time, where this could be, sometimes it would be less, it would be about average case of n over 2. So if you're dealing with an average case of all these, well, then maybe this looks more appealing. At any rate, if I expect to do about the same number of insertions and removals, if this is an average case of n over 2, and this is even in the best case going to be strictly n, the point is I still basically am going to have a constant time plus a linear time operation. There's, variances and constants and such, depending on which particular situation we pick and how many find mins we might do. But essentially, if our situation is going to be that we expect to do some insertions and some delete mins and expect to have them roughly balanced, that anything you insert into the priority queue eventually gets removed. And if you're not doing too many, just looking at the front element type operations, what you tend to expect would be that, okay, I can insert and then delete min, and depending on whether I choose sorted or unsorted, one of those will be constant, one of them will be linear, and so the total work on a value would be linear. And even if I do a few extra find mins, if I add some more linears to that, it's still linear. If I add some more constants to that and it's a sorted list, it's still linear. Essentially, we would expect about a linear amount of processing on each element, because one of the operations, possibly 2, are going to be linear. And so you can only insert once, you can only remove once, you can do find min many times. So it could be worse than linear if we use the unsorted list and you do a lot of find mins. But other than that particular situation, we'll end up with about linear time processing on each element. So the question is, can we do better than that? And we did look at a logarithmic-based structure with an AVL tree. We knew we could insert in log of n time. Now the question is, what about delete min or find min? We ask, where is the minimum? And the minimum in an AVL tree is the leftmost element. That's why we said when talking about a binary search tree that if I want to do a 2-child remove, I find the in-order successor of that value I want to remove, and that was always the minimum node in the right subtree. The in-order successor was the minimum node in the right subtree, so we said it's the leftmost value in the right subtree. Likewise, the minimum of the whole tree is the leftmost value, because you're always saying, well, whatever node I'm at, I want to go to the left because what I'm looking for is less than this, until finally your left pointer is null, which means there's nothing less than you. And so traversing down the left side of a tree, if it's balanced, is going to be log n. And then removing that value will likewise be log n. And so both of those are log n as well. And so if I expect one insert and one delete min, then that's going to be log n plus log n is log n, which is better than the linked list version. So at this point, unless you're super tight on memory and can't afford the extra pointer per node that an AVL tree would have compared to a linked list, then probably the AVL tree would be the better choice out of the two of them. Now you can also consider things like a skip list, which would allow you to traverse. You could do an insert into the skip list. We said in logarithmic time in the average case, linear in the very unlikely worst case. Likewise, to remove a value, to search and remove, or to just find the minimum, those would be right at the front of the list. So that those could be considered, constant time, but you'd have to readjust some pointers then, and as far as levels, if that node was a high level. So that could still be worst case for removal anyway. Worst case logarithmic time, because you have a whole array of pointers to your various levels, and if you're simply pulling off the front node of a skip list, you might need to change out those pointers. So even though you don't need to search for the node, you will potentially need to change the various pointers to the array of head pointers to the various levels of the linked list, and that can chew up some time as well. However, the point is that so we can perhaps say that on the average we have half log n or whatever, and or actually on the average case we might even have just 1 or 2 pointers to change there for delete min. So we can say, okay, a skip list might have a very fast delete min and a logarithmic insert. The issue, what we'll be looking at will be that instead of dealing with those the constant factors inherent in some of that, the higher log n cost or whatever, which we'll have, we do have a third tree type structure that we have not really looked at yet to take care of this. We've got the AVL tree that would give us this performance. A skip list would give us logarithmic performance for at least insert and potentially logarithmic performance for delete min as well, though find min would be constant time. We can have a structure that does something similar for us. That's sort of a tree-based issue, just like skip lists we said could be thought of as balanced binary trees in the expected case at least. And so the problem is that worst case, and so otherwise they'd be comparable to AVL trees. But if we're going to use a skip list, we potentially have a linear time for insert. We expect logarithmic. There's this potential for a logarithmic time with delete min, but we at least avoid the linear because we're not removing the first node. But we can do even better than that while also saving memory, using a structure that's uniquely suited to what we want to do here. So we're going to stick with the logarithmic time ultimately. So the linked list was providing us linear time. The AVL tree was logarithmic in the worst case, and the skip list would at least give us logarithmic in the average case. What we're going to look at now will be also logarithmic in the worst case. And the idea is known as a complete tree, which you may have seen in a discrete math course, but we haven't really talked about use of it in any implementations here. The concept is one of it's going to be a perfect tree some height. Perfect tree being a tree with all possible nodes at that given height. So there's a perfect tree of height 1. There's a perfect tree of height 2. There's a perfect tree of height 3. And so on. The idea is that you've basically got every node except all the leaves are pick some depth. All the leaves are at that depth. And all the other nodes have exactly 2 children, and that pretty much fills out the entire tree. It's every possible node, with tree having given height, every possible node with a tree at that given height. So a complete tree will be perfect down to some height, and then maybe it ends there. So every perfect tree is also a complete tree. Otherwise, children added to a new bottom level from left to right. So in other words, we will say, I would add this child first, and this one, and then this one. And I'm only drawing dotted lines so that it's clear, the separation between the perfect and the complete tree. But that's what we've got here, is if we're adding children, if we don't have a complete tree, or when it comes time to add more children, we have to add them from left to right across the bottom level. So for example, if I now choose to toss in this as well, then that's not a complete tree. So we don't want to do that, because we've skipped all the nodes in between this one and this one. I can add that child, but first I have to add the 2 children of that node, the 2 children of that node, and the 2 children of that node. So the idea is we're adding elements from left to right across a row, and when that row fills up, we're back at a complete tree, but now of depth 4, and then we now start in the next level from left to right. Basically, imagine a perfect tree of however deep you want to go, and do a level order traversal on that tree. So you'd have node 1 here, those would be the next 2 nodes, those would be the next 4 nodes you'd print, then those 8, then those 16, then the 32 below them, and so on. Imagine doing a level order of such a tree. What would be the order in which you get the nodes? That's the order in which you would add the nodes to a complete tree. So the root's, of course, going to be the first node. The left child of the root would have to be the second node. The third node you add would have to be this one. That would be the 4th node you would add, the 5th node, the 6th node, the 7th node, and so on. So we haven't written any values in the nodes yet, but as far as just looking at the structure, if I tell you you have a complete tree of n nodes, you know exactly what the structure looks like. Because there's one, no matter what n happens to be, there's one tree with that number of nodes. The tree with those 3 nodes and this one is the only possible complete tree of 4 nodes. Those 6, that's the only possible complete tree of 6 nodes. The first 3, and then 4, 5, and 6, because you're adding from left to right on the bottom level. What I've got drawn here, minus this incorrect node that I've written no under, is the only possible complete tree of 18 nodes. We've got 15 in the first 3 levels, that fills out the first 3 levels, and then 3 more added from left to right on the bottom. So no matter how big the complete tree is, there's only one possible structure it could have. So I tell you, you have 18 nodes in a complete tree, you know it looks like this. There's no other way around it. Like I said, getting rid of that, of course. You know it would look like that then. There's no other way that could be dealt with. And this is going to be helpful to us because it means we can rely on a consistent structure for the complete tree, because we always know what gets added next. I know the next value that gets added is going to go right here. And when we actually implement this, it's going to knowing that's going to be very helpful to us. Knowing that I don't have to worry about, what if I add here before any of these? That can't happen. And so the question is, well, why is this particularly relevant to us? And the answer is, I'm going to draw a smaller complete tree now. Here's the one complete tree of 10 nodes. It's the only possible complete tree of 10 nodes, because if you have 7 nodes, you have those 7 here, and then 8, 9, and 10 get added there. Now, let's number these nodes in the order in which we want to add them. That's the first node, that's the second, that's the third, 4th, 5th, 6th, 7th, 8th, 9th, and 10th. Testing. The microphone just cut out on me, sorry. I don't know why, the battery's fine, but it just blanked out. So I'm glad I realized that before giving the whole rest of the lecture. Okay, let me start again. The when we deal with this tree, what we've done here is we've numbered the various nodes. And this is the order we would add them in, so I know there's no other possible tree that has 10 nodes in it. That's the only possible way to structure a complete tree with 10 nodes. In addition, I'm going to give you a moment and pause, and so you can pause the tape once I ask the question and try and figure it out. Take a look and see if you notice any relation between parents and children in terms of these numbers. And I'll pause for a moment if you want. Okay, so if you've now started things again, the issue here is if you notice for example, every left child is always double the number of its parent. 8 is the double of 4, 4 is the double of 2, 10 is the double of 5, 6 is the double of 3. And though I'm not going to take time and prove this here, you have a formula here where you say if you want to know the left child index of a node I, you can simply say 2 times I. Given a node number, I mean, it's not the number stored in the node, but if I'm going to sort of deal with these as indices on this tree, if I have a particular number associated with this node, and I want to know the particular number that would be associated with the left child, I simply double it. And of course, that means since the right child is always the one right next to the left child, in that case, we're sort of doing this, numbering these in a level order manner, so the right child's always right after the left child. That means the right child is always going to be 2 times I plus 1. And we can see that in the picture as well. 2 times 4 plus 1 is 9. 2 times 2 plus 1 is 5. 2 times 3 plus 1 is 7. And since we have these relationships where you're basically doubling the parent to get the children, it's a little more than double to the right child, that implies that we could divide by 2 to get the parent. So with a left child, you exactly divide by 2. 8 divided by 2 is 4. 6 divided by 2 is 3. 2 divided by 2 is 1. With the right child, if you divide by 2, you'll get the parent plus 0.5. And so what you want is to round down to the nearest integer. We can use the floor function. That notation simply means that we're dealing with the greatest integer less than or equal to this value. And so we're saying, well, in this case, if I get any integer, then that's my result. And if I get any integer plus point anything, we get the integer. Basically, it's truncation, which C++ would do automatically, as would Java. And so if you do integer division, an integer divided by 2, and you get something 0.5, since you're doing integer division rather than taking 82.0 divided by 2, 83.0 divided by 2 would give you 41.5. But if it's just 83 divided by 2, then that's 2 integers. That means you're doing truncation, and it means the result you get is only an integer. And that's how C++ would work in that situation. So if I ask you what 7 divided by 2 is, 7 divided by 2 is 3, because the integer division truncates the 0.5 when your real answer is 3.5. So that's all we need to do. We don't even really need to code the floor function. We could simply, in C++ code, say I divided by 2. And that'll get rid of the 0.5. And so that works for any case then. 8 divided by 2 is 4. 9 divided by 2 is 4.5. With the 0.5 truncated gives you 4. Likewise with any other node in the tree. So these are your 3 formulas that enable you, if you know the nodes associated, or the numbers associated with these nodes, to traverse around the tree quite easily. You if you're at a given node, you double the index of that node to get the left child, you double it and add 1 to get the right child, you divide it by 2 using integer division to get the parent. And in fact, these are even faster, because if you do multiplication by 2 or division by 2 in C++, what this is bit shifting, which actually you do indeed have shift operators in C++ that are the same symbols that are used for input and output, because it's always clear from context what you mean to do, but you don't really need to deal with those. A compiler often will optimize that for you. So if you're multiplying by 2 or dividing by 2 specifically, that's just a bit shift. For example, if I wanted to say I have here the number 10, so this is 8 and 4 and 2 and 1. There's the binary number 10. I have 8 plus 2. If I want to divide by 2, I shift it this way, and I put in a leading 0 here, and then I get 1, 0, 1, and then that last 0 was lost when I shifted to the left. So if I'm trying to represent these in just 4 spaces, then I can shift these numbers to the right. I lose the front 0, and then I just toss in some random 0 at the end. And here's 10, and that number's 5. And likewise, shifting the bits this way, if we have 5 and we want to multiply it by 2, we shift the bits that way, we lose that 0, and then we'd stick in a 0 or a 1 at the front to add 0 or add 1 to the result. So 5 times 2 is 10. So a compiler can often optimize, or you could code it yourself to use bit shifting, optimize multiplication or division by 2, and say instead of going to the multiplication hardware to do this, simply do a bit shift, and that's a very quick machine operation. And as a result, traversing around this tree is going to be very, very fast. We'll spend almost no time doing each transition because I can go from this node to here to here to here, or at least jump around the numbers that represent those nodes simply by doing bit shifting. Take the number 8, and then shift to the right, shift to the right, shift to the right, and we're at 1. So it'll be very easy to jump around this and convert our index to the other relevant indices for our children or our parent. And so what this means for us, because we have the ability to index nodes in this manner, what we have the ability to do then is to represent this as an array, where if I have here, there's 1, 2, 3, 4, 5, 6, 7, 8, 9. That's my complete tree, for example. I can represent this as an array and say here's cell 1, here's cell 2, here's cell 3, cell 4, 5, 6, 7, 8, 9. And then we might have extra cells in addition, and so we'll need to keep track of exactly what our size is. So we say it's 9 right now, and then 10 and 11, these would all have values in them. 10 and 11 would be then, for further storage, just like we did for the stack, where we said, we can have a array for the stack, and we don't need to increase the stack by 1 cell with every insertion. We simply have a chunk of memory, and once it fills up, we can then create a new array, double the size, and copy everything into there. And so often we'll do that. We'll have some array allocated in advance, and we'll just, as we insert into the complete tree, add value 10 and 11 and 12 and 13 and so on. We simply now take up more of these cells to the right, just like we did with the push operation in a stack, until we're all finished and the array is full, and then we can increase the size of our array. So we have this parallel here, where whatever was stored at cell 1 could be stored here, and whatever was stored at the left child of the row would be stored in cell 2, and whatever was stored at the right child of the row would be stored in cell 3, and so on. And normally we wouldn't represent a tree using an array for 2 reasons. Firstly, we need to know what nodes point to what. And so if we're going to represent a tree as an array, I would need to say, well, 1 has pointers to these particular cells, and so on. So we would need to store the pointers anyway, because otherwise there'd be no way of knowing which nodes pointed to which other nodes. But we're okay here in that regard, because the particular way the complete tree is laid out, I simply double an index. So I can say, if I'm at cell 5 and I want to go to its right child, I double 5 and add, or actually we don't even have that in this tree. Cell 3, and I want to go to its right child, I double 3 and I add 1. 3 times 2 is 6, plus 1 is 7. I jump to cell 7. Which is, if I had built this tree like this, exactly what I would have done. I would have followed 3's right pointer and went to 7. Here I can just say double 3 and add 1, and I get to 7. So I don't need to store pointers once I use the array implementation, where with other attempts to implement a tree in an array, we would have had to store some reference to what other indices in the array, what cells in the array held our left and right children. And so if we're going to have to use those sort of quasi-pointers anyway, we may as well just build a tree. The other issue is that if we want to insert in various places in the tree, we'd have to do a lot of shifting normally, Because now we might say, well, if I'm keeping these in some semblance of an order, I might want to stick some value in here. Or I might just dump it in a new cell and point directly to it. That might be easier. But there may be, depending on exactly how you're trying to rework things and how you're trying to make those pointers work, you might end up in some cases saying, well, I'm going to represent a tree in an array, trying to keep it in some ordered manner. I'll end up, sticking values into cells here and having to shift everything over. Where here with the complete tree, I know the only additions I'm doing are on this end. And as I do removals, I'll be removing them from this end. So it'll work very much like push on a array implementation of a stack, where we simply say keep track of your most recently used element, and then when I want to write into the next element, I increase the size and write into the A of size, if this array is A. So it's very easy to do here. My insertions just work this way, my removals work the other way, and there's no need for pointers because those math formulas tell me what the parent and left and right children will be. And so, though for our examples, I would draw pictures like this, this array is the real implementation. This is conceptually how you might choose to view things to make conceptual understanding easier, but this is the actual implementation that we'll make use of. The array, we'll implement a complete tree using an array. Now, the last thing to mention is the idea of partial ordering, because it's still a little bit unclear how any of this would help us for a priority queue. And we say a tree is partially ordered if at every node that node's value is less than the values of children. So maybe we have here, for example, 3, and here's 7, and here's 100, and here's 9, and here's 8, and here's 106, and 120, and then maybe off of 9 I've got 17 and 12. There's an example of a partially ordered tree. 9 is less than 17 and 12, 7 is less than 8 or 9, 100 is less than 106 or 120, and 3 is less than 7 or 100. So it's a partially ordered tree because at every node, if there's any children of that node, the node's value is less than the values of the children. And now you'll notice a few things about this. Firstly, it doesn't matter whether the left or right child is less. In this case, the left child is less. In this case, the left child is less. In this case, the right child is less. In that case, the right child is less. So whether the left or right child is less makes no difference whatsoever. Additionally, we're not making any sort of commentary about levels. We're not saying, oh, if it's in level 3, it's greater than level 2. Here's 2 nodes that are of depth 3, and they're both less than this node over here that's of depth 1. So there's no relations between the subtrees. There's no relations between individual children. The only thing that matters is that at a given node, at every node, that node is less than its children. Everything else, there's always people tempted to put more restrictions on this because they think that's how it should be. Don't. And that's why I wrote that example, to show things like that to you. That even as deep as you go here, they're still less than what's up there. It's not a problem. These 2 subtrees have nothing to do with each other other than that their roots can't be less than 3. And in fact, you might notice that, well, since 7's children have to be less than 7, and their children have to be less than them, and their children have to be less than them, what we actually get is that it's less than the values of its children and other descendants. I'll put that in parentheses. That just sort of follows from the definition. If every node has to be less than its children, then every node is also, I should say, proper descendants. If every node is less than its children, then every node is going to be less than all its proper descendants as well, which was descendants other than yourself. So we're saying since 3 is less than 7 and 100, and they have to be less than their children, likewise, then by transitivity, 3 has to be less than their children. Because if 3 is less than 7 and 7 is less than 8, 3 must be less than 8. And likewise, if 7 is less than 9, then 3 must be less than 9, and so on. So if 3 is less than its children, the children are less than the grandchildren, so 3 has to be less than the grandchildren. And you can continue on that and eventually arrive at the conclusion here, that any subtree root is going to be there's going to be less than everything else in that subtree. And so the root of the entire structure is the minimum of the tree. So when you go looking for the minimum in a partially ordered tree, then it's at the top. Because by this very definition, if every node has to be less than its children, the minimum has to be the thing that is not a child of anything. And so that would be the root would be the minimum. Oh, that said, we now reach our implementation, which is a heap. So when I said that the sorting algorithm based off priority queues is called a heap sort, that's why. Because the implementation we're going to use is called a heap. And a heap is a partially ordered complete tree implemented as an array. Partially ordered, as we just looked at, it's going to be complete. Not every partially ordered tree has to be complete. I could have taken this picture and I could have said, well, let's make a right child greater than 106, say 115. That's what you see there is a perfectly reasonable partially ordered tree. It's not a partially ordered complete tree, but it is a partially ordered tree. There's no problem there. We're saying not only does it have to be partially ordered, it also has to be a complete tree, like our first example here was before I just added the node I just added. And then it's not going to be the conceptual tree, it's going to be implemented using an array like we talked about already. And that's a heap. We're going to be looking at how our operations for priority queues run in heaps, but basically this is such a common implementation that it pretty much is synonymous with priority queues. When people say priority queue, they mean heap. Don't get confused, by the way, we also, when we talk about heaps, when we talk about dynamic memory, it's just an unfortunate quirk of computer science that there happen to be two different ideas for the same word. People doing memory management called it a heap, and people coming up with this implementation called it a heap. And so they're both called a heap. And it's almost always clear from context what people are talking about. But at any rate, this is a different heap than the memory management concept we talked about. Those are two different concepts with the same word. And this is the one that's most important for you. The issue then is that we basically, when we say priority queue, we mean heap. And when we say heap, we mean priority queue. The two are almost synonymous because this is the implementation that's best for a priority queue. And we'll talk about why. So by way of an example, let me go ahead and draw out such a tree. We will say I have here 8, 7, 11, 17, 24, 20, and we have here 18 and 9. And it's okay. 7 and 8 are less than 2. 11 and 17 are less than 8. 8 and 19 are less than 7. Yep. So that's a complete tree because we've got it's perfect, and then in the bottom level, nodes added from left to right. It is a partially ordered tree, as I've just confirmed myself. Every node is less than its children. And now we're going to say, well, that's just a conceptual model. This now makes it a heap. We won't really create that. That's just the picture I'm drawing. What it really looks like is this. Index 2 has the value 8. Index 3 has the value 7. Index 4 has the value 11. Index 5 has the value 17. 18 for 6. 9 for 7. 24 for 8. 20 for 9. And then we have perhaps 10 here and 11 and however many other values. Your size here is 9. And so this array is what we'll keep track of. Our data structure will have a pointer to this array, and this array will then be our implementation. So don't think the tree is, or that we're keeping track of both of them at once. The array is our implementation, let's call it A, and the tree is just going to be there to aid our conceptual model. So, that said, we need to deal with insert. And let me actually put that back for a minute. Our highest priority when dealing with insert is going to be to make sure it's a complete tree. Certainly it has to continue to be implemented using an array, because if this is my implementation, adding a value somewhere else in the array doesn't change the fact that it's an array. I don't write into A of 10 and suddenly this deletes and that tree shows up out of the blue. So if we've got an array implementation and we're inserting values into it, it'll continue to be an array implementation. That part's easy. The question is an array implementation of what? So we want to make sure it's a complete tree as well. We don't want to insert into A of 11 before A of 10, so I'll insert into A of 10 when I insert. And you ask, well, wait a minute, what if that doesn't work? We'll talk about that in just a second. But I'm going to want to insert into A of size plus 1, or rather increase size, in this case from 9 to 10, and then insert an A of size. The lowest unused cell before the insertion is where the insertion goes. And that'll make it a complete tree, because now you're using the cells 1 through 10. Hopefully it's clear that because the way we've numbered these, if you're using the cells 1 through whatever, with no gaps and no extra cells off to the side that aren't in that sequence, then we're okay. The only cells we want to be using are the ones from 1 through n, all of them in that range, none of them after n. And if that's the case, then we've got a complete tree. So, since we've got a complete tree, the issue is then, well, given that we have a complete tree and it's implemented as an array, we now need to make sure it's partially ordered. And that's where a little bit of work comes in. But implementing it as an array is easy. You just don't change the data structure. And making it a complete tree is simply a matter of inserting into the value after the last one that's actually in your heap. And now we need to make it partially ordered. So we can start insert out with that kind of a discussion. We can say, well, for insert, the first thing you do is write x into A of size plus 1, and then you want to increase size. So then what you want to do is you're going to want to percolate up. I'm going to quickly resketch that tree because I want to keep the slide for Charles to scan in. If we have here 2, 8, 7, 11, 17, 18, 9, 24, 20, and here we have an array 2, 8, 7, 11, 17, 18, 9, 24, 20, 1, 2, 3, 4, 5, 6, 7, 8, 9. Same exact slide as before, except I guess now I'll have it in cell 12, and that doesn't matter. And let's say that what we do is we insert the value 4. What happens? Well, based on what I just wrote on that insert slide, the first thing I do is I put 4 in this cell, change my size to 10. So I do that to the array. Conceptually, what has happened here is I've inserted 4 as the left child of 17. And now we've got a problem. It's an array implementation, it's a complete tree, but it's not partially ordered. 4 is less than 17. And what can we do about that? Well, what we can do about that is fix 4 and 17, because the rest of the heap is okay. Again, this is the implementation, but it's easy to point things out conceptually. This is still a legal heap. This is still a legal heap, except for the 417 problem. The whole thing is fine. So let's swap up 4 and 17. And say, well, since 4 is less than 17, between the two of them, 4 should really be the parent and 17 should be the child. And the way we do that is we say, well, I know I just inserted into the cell size, that index, 10. So use the parent function. Parent function is always your current index minus 2, or divided by 2. 10 divided by 2 is 5, so I know that's the cell I look at. And so from here I can say, well, from 10, look at 5. And I say, well, what is at A of 5, this array being A? What's at A of 5 is greater than what's at A of 10, so what I will do is swap these values. And 4 would go here, and 17 would go there. So we still have a problem because now 4 is less than 17, but it's not less than 8. Let's swap again. Let's say, well, 4 is still less than its parent, so we go ahead and swap those. And the way we handled that in the real implementation was 5 divided by 2 is 2, because our integer division rounds down. So 5 divided by 2 is 2. The value there is 8. 8 is greater than 4, so we can go ahead and swap 8 and 4. And then finally we say, well, what's the parent of 4 now? The parent of 4 is 2, and since 2 is less than 4, we can stop. We don't need to swap 4 up again because now it's okay. So what we've got here is, well, you notice this whole heap now is okay. The reason we were able to swap 4 and 8 is we already knew for sure 8 was less than its children. The whole thing was legal to start with. And so 8 must have been less than 11 and 17. Now if I swap 4 and 8, well, if 4 is less than 8, and 8 is less than 11, then 4 must be less than 11 as well. In addition, we know 4 is less than 8 because we wouldn't have done the swap otherwise. And so we know this setup is okay. Since 8 was less than 11 by virtue of being above 11 as a parent of 11 earlier, and I've just checked that 4 is less than 8, therefore by transitivity 4 must be less than 11. And so when I swap upwards, everything from that point downward is okay. I swap 8 and 4. Now anything from 4 downward is fine. And so if eventually we ended up swapping to the root, for example, if I had inserted 1, I'd need to do one more swap here. Eventually we swap up to the root, and that would be the last swap we'd have to do, but then everything from the root down would be fine. That's how insert is. When we insert, what we're doing is saying, I want to loop, and then, let me not do anything there. I want to loop, and I say, if you are at the root, meaning you have no parent, or your parent is less than you, then we stop the loop. We'll be done. So if you're at the root, if you are the root, you don't have a parent. There's nothing to look for. Likewise, if you look at your parent, you have one, but that parent's less than you, then you would stop. The only other option here is to say swap with parent. And that's pretty much your insertion operation. I'm going to keep swapping with parent, and then swap with, however we deal with our tree. Say, well, down here I had 4. I swap with its parent and got 17. Then I swap with its parent and got 8. And the only reason I didn't swap with its parent is because 4 is indeed 2 is less than 4. And that was our condition here. We stop when our parent is less than u. We stop here because 2 is less than 4. Or if we were at the root. If this had been 1 and I swapped 1 with 2, then I'm at the root and I stop. So in the cases where we're supposed to stop, we leave the loop and we're finished. And here's where that happened. Now that the parent 2 is less than the value 4, we stop. We leave the loop and we're done. Otherwise, you'd swap upwards. And so we've seen now, this is the code or it's the pseudocode anyway, and on the previous slide we saw the result. And that's really all there is to insert. What I will leave you to do before section will go over the code for this, but I'll leave, I think, a good exercise for practice for you would be to go ahead and, before you watch the section video, try and figure out actual detailed code for insert yourself. But at any rate, that would be how you would do insert. Now I'm going to redraw that whole tree one more time. Remove is exactly the opposite situation. So here's our tree again. 2, 8, 7, 11, 17, 18, 9, 24, 20. And then here's the array. Blah, 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 blah. The idea behind remove will again be as we started insert. What we want to do is we want to keep track of, we know for sure it's an array implementation, that's automatic. We likewise want to make it a complete tree. We have here the size at the moment is 9. So if I'm going to do, this isn't really a remove, I keep saying remove. We of course mean delete min, but I've had this mental block for years where I keep saying remove and hopefully everyone knows what I mean. But anyway, I mean delete min. And if I keep saying remove as I talk about this, I'm sorry. It's just a weird mental block where I know what I'm trying to say and I never say the right word. So I just warn people about that as I talk. So that said, what you've got here now, if I want to do a delete min, I need to get rid of 2. And it's not enough just to say, oh, return A of 1. Certainly that's where 2 will be. And that's why find min is easy here. For find min, I just say return A of 1. I don't need to make any alterations. But deleting it's going to be a lot like when we had a linked list implementation of a stack. For pop, we had to remove the first node of the linked list. And what that required was not just returning the value in the linked list, because we had to remove the node. So what we had to do was take our value, save it somewhere in a temp, then we could actually get rid of the value itself, and then we could return the temp. And that's what we had to do back when we had a linked list implementation of a stack. We said popping from that stack was basically removing the head node of the list. What we had to do was say, well, save head arrow element in some temp field. Then you could delete the first node and reassign and readjust the list, and then return that temp you had stored. And we'll do the same thing here. When we deal with delete min, we're going to say, well, temp is assigned the value A of 1, and then down here at the very end, we would return temp. So that said, two is safely stored away. The question is, what do we do next? And the answer is, well, like I said, we know it's an array implementation. What we need to ensure is that this remains a complete tree as well. And if it's not a complete tree, then we have problems. And so that's why we're going to ensure that. And then, just as with inserts, once we ensure it's a complete tree, then what we're able to do is then adjust things and fix the partial ordering. But the partial ordering is the last for both insert and delete min, and that's a helpful way to remember it. The partial ordering is the last thing you worry about. You worry about making sure it stays a complete tree first, then you worry about having the partial ordering set up nicely. And so what we have here now, if we look at the situation, is I want to delete min on 2. Unfortunately, the problem I run into is that the node I need to delete is 20. So it's this value I want to get rid of, and I can safely store it somewhere else, but I need to get rid of it from that node. That's an empty node now. But the real node I want to get rid of is 20, because a complete tree is supposed to get rid of that node. So what we really want is to say the size is decreased to 8. Not 10, 8. And this node is gone. So this will be what matters. That will be the last cell that matters. This will be the real portion of the heap. And 20 is sort of left out in the code, which is a problem because now, this cell is blank, and that cell needs a value, and that value needs a cell. And there's always one of the suggestions for fixing this is then to shift everything over and say, well, 8 moves to cell 1, 7 moves to cell 2, 11 moves to cell 3. Aside from the fact that's linear time, that's a bit unappealing because it doesn't really fix the problem. In fact, it messes up the heap tremendously. Let me kind of show a quick example of that. If I had this situation where I have here, say, 2, 100, and I have here 7. Actually, I think it's the other way around I want it. 2, 7, 100, 9, 8, 102. If I did a shift of these, remember the array will be 2, 7, 100, 9, 8, and 102. If I do a shift over, I get 7, 100, 9, 8, 102. I shift these from cells, 2 to n to 1 to n minus 1. Well, if you draw that out, you have 7, 100, 9, 8, 102. That is, shifting 100 to be that parent when 8 was here because it was less than 7 gives us that situation, which is not legal. And here you can see 8 is not supposed to be less than 100. Or at least you shouldn't arrange, because 8 is less than 100, you shouldn't arrange the heap like that. And so the problem with that then is that the heap is messed up in a number of places. The partial ordering is potentially messed up in a number of places. We may not know where they are. We'd have to find them. And so that's going to take at least linear time to correct, as well as the whole shifting would have taken linear time to begin with. So shifting everything over is not an option. Instead, what we would prefer to do is to say, what if I just take 20? I have a value without a home. I have a home without a value. Let's take 20 and write it into this cell. Or in other words, this value gets written up here. Now I have, I don't need to worry about cell 9. 20 has been safely stored in cell 1. And yet, the issue is this entire heap, which was perfectly legal, is still legal. And this heap is legal. The subtrees are okay. They're complete trees and they're partially ordered. And all that matters then is the top part. So we haven't messed up the partial ordering all over the tree. What we've done is only said, well, this top node is out of place in the same way the bottom node had been out of place when we did the insert. And now we need to move the top one down until it finds its home. But the rest of this is okay. So the only thing that needs to be corrected is how 20 relates to everything else. And so that's what we'll take a look at. We can say the short form of this is take a look at 8 and 7. Which one is one of them less than 20? And indeed it is. So we can't keep 20 at the root. What we do instead is say, well, the lower of these two is 7, and that swaps with 20. And now the lower of those two is 9, and that swaps with 20. And we've got that set up there. Or in other words, what we do with delete min is we say, after we've stored the 10th away, we will write a of size into a of 1, and then say size minus minus. And once that's done, then that's the situation we had before I swapped downward, where the size had been reduced to 8, and 20 was sitting in a of 1, and then 2 is in a temporary variable ready to be sent back. And now it's simply a matter of percolating 20 down the tree. So our loop here is going to be, what we will do is if either value is less than both children, I should say less than all children. So if your value is less than all children, or you have no children, then again, you exit the loop. Otherwise, swap with minimum child. So you've got a loop here that will say, if it turns out that your value is less than all its children, then you're done. I mean, there's no problem there. The only value that's out of place was what we moved to the top. In the previous example, the only thing that was out of place was 20. If it had happened that this had been 6, well, it would be less than 8 and 7. We know this entire structure was okay. We knew this was okay. And now if 6 was up there, 6 would be less than 8 or 7. We'd be fine. So when the value is less than all its children, now the tree is partially ordered as well, and you can stop. Otherwise, if you have no children, the same thing will be the case. So these are your two conditions here. I should really sort of circle these. If you don't have any children, then there's no children to compare to. You're still okay. It's still partially ordered. There's just no chance of your value being less than its children because you don't have any children to be less. There's no chance of the value being greater than its children because you don't have any value to be greater than. And if you can't stop, then you swap with your minimum child, and of course you loop again. And that's exactly what we did here. We said 7 is not less than all its children, but it does have children. So we swap with the minimum child, which was 7, and then we continue with that process. And then what we would have done down here would be that same thing. We would have said, well, what are the children of index 1? Well, they're 2 times 1, and 2 times 1 plus 1, namely 2 and 3. So we do have children there. They do exist. And the 20 is not less than both of them. So we swap 20 with the minimum child, and we continue. And we say, what are the children of 3? Well, they're 3 times 2 and 3 times 2 plus 1, namely 6 and 7. And both of those do exist, and 20 is not less than both of them, so we swap 20 with the minimum child. And we say, well, there we go. And likewise, we know here, we're saying, well, since 9, for example, when I decide swapping 20 with 18 and 9 and looking at those, I say, well, I know 9 is less than 20 because we just compared and we said, well, 20 is not less than all the children. Let me start that over. As far as 18 and 9 goes, because I'm picking the minimum child to swap with, I know I've got the smallest child. So 9 can rest comfortably up in this spot. 9 can be the parent of 18 because 9 was the minimum child. Out of the 2 children, we're picking the smaller one because then that smaller one can safely be the root of that node. So the smaller one can be the parent of the larger one. The previous phrase didn't make sense, root of the node. We can be the parent of the other node. When you have 2 children, the minimum can move up. That's why we pick the minimum child. Likewise, if we are not less than both children, 20 was not less than both children, so it's got to be greater than at least one of the children by definition. Well, certainly if it's greater than at least one of the children, it's greater than the minimum because the minimum is the smallest child. If you're not greater than the minimum, you're not greater than anything. And so, likewise, as we had a look at the situation with insert, we look at it here with deletement as well, and we say, I know it's safe to swap 20 and 9 because that puts 9 as the parent of 18 and 20. We know 9 can be the parent of 18 because 9 was the minimum child when 9 and 18 were the children. So we know 9 is less than 18. And likewise, we know it's safe to have 9 be the parent of 20 because if 20 wasn't, 9 being the minimum, if 20 wasn't greater than 9, then 20 wouldn't be greater than any of the children, and then we would have said 20 is less than the children, and we would have stopped without a swap. So we know whatever numbers we happen to have here, if we do say that that 20 is not, that the parent here is not less than both children, and we need to swap the minimum, then we know the minimum here up here that lands up here will be less than both the other child and what is just swapped with. And then we say, well, now 20 is at cell 7. The left child and right child are 14 and 15, which don't exist. And so we're fine. So we'll come back to that don't exist in a moment. But that's the idea here. So that's delete min. If you are less than all your children, or you don't have any children, you can stop. Otherwise, you swap with your minimum child and you loop again. And then when that finally ends, you return temp. Likewise, it's to your benefit to try and tinker with that and write that code out yourself. That's just the rough pseudocode. But to write that code out yourself before seeing it in section. One thing I do want to point out is the idea of existence. When we say, well, how do we know the children exist? Well, I pointed and said, well, 14 and 15 don't exist. They're not part of the array. But likewise, we don't want to think of 10 or 11 existing as either, because 10 and 11 would be the children of 17, and they don't exist. When we say a node exists or not, what we're saying is it's part of the size of the array. So what we can really say is, for an I, if 2 times I is greater than the size of the array, if we say my left child would be at such and such an index, 2 times I, and that's beyond the size of your heap, not the size of the array, but the size of the heap, then you have no left child. And that's what we saw here. 20's left child, since 20 was at cell 7, 20's left child would have been 14. 14 is greater than 8, so there's no left child. And therefore, if there's no left child, certainly there's no right child. If 2 times I is equal to size, that means our left child is in the heap, but it's the very, very last node. So that in that case, you have a left child, but no right child. And we see that here. 11 is cell 4. The left child of 11 is 2 times 4, which is at 8. We can see that here. The left child of 11 is at cell 8. Since the size is 8, that means the index of 11's left child is the very last cell that's actually in the heap. And you can see that here by comparing the size. Or you can say, well, I've gotten rid of this node. So yeah, clearly even in the picture, 24 is the last cell in the heap. And so because the index of your left child was equal to the size, that meant the index of your left child was the very last cell that was considered part of the heap, and therefore the cell next cell over would not be part of the heap, and that means you don't have a right child, which we don't in the picture because we got rid of 20. And of course, likewise, if 2 times I is less than size, then that means you have a left child and a right child. It may turn out the right child is the very last element. 2 plus I plus 1, 2 times I plus 1 could have been equal to size. We don't care. When we're just concerned at a given node of saying, what are my left and right children? Whether that right child happens to be the very last cell in the heap or not affects nothing as far as me comparing to my 2 children. It will affect later calculations. But if I say I look at my left and my right children and they both exist, that's what matters. And if nothing exists after my right child, I don't care. I'm only concerned about looking at my left and right children. So those are the 3 conditions you'd concern yourself with. This tells you that your index has no children. This tells you it has 1. That tells you it has 2. So that might help you out a bit when writing the code for delete min. Now, one last thing worth mentioning, or a couple last things worth mentioning. When we talk about running times, hopefully it's clear that in the worst case, the running times will both be logarithmic. Worst case. Let me write this. That's all you need to know. I'm going to talk about the average cases as well, but I'm concerned just about you knowing the worst case for the exam. They'd both be logarithmic. The reason being, let me just show the picture very quickly. For a removal, for delete min, if I need to percolate downwards, if I need to shift this downwards, I might shift all the levels of the tree. I might have swapped with the left, I wouldn't have here, but let's say this had been 9 and that had been 8. Then I would have swapped with 8. So I might have swapped with here, and here, and here, and ended up all the way down in the bottom of the tree. In fact, as things are, I ended up 1 level away from the bottom of the tree. So the higher this gets, the worst case will involve us swapping many levels all the way down to the bottom of the tree. And certainly a swap is constant time, and this being a pretty well balanced tree, you'll have height log n, and so log n times constant time is log n. And so you're basically doing constant time work for every swap as you make your way down a log n height tree. And likewise for insertion, the same thing applies. If I'm going to insert, then I'm going to be shifting upwards, and we saw that before. I say, well, I insert down here, and in the worst case, what I'm inserting is the new minimum, so I would percolate upwards until I hit the root. And again, that's a swap up per level up to the top log n levels is worst case log n. Now, as far as an average case goes, the average cases here will be a little bit different. For insert, we don't expect to have to move too many levels in the tree. And the reason is, if you consider a tree here, consider just a perfect tree of, say, height 3. Notice that the entire bottom level contains more nodes than all the levels above it combined. And so if that row happened to not be completely filled up, if we had this picture instead, where we have, perfect down to 2 levels, and then maybe only 3 nodes here, that won't necessarily be the case. But certainly, because if I was to cover that bottom row up, now the bottom row that's uncovered in this case has more nodes than everything above it together. Certainly, if I throw those in, these 2 rows together have more nodes than everything above them. So if it's a perfect tree, you can actually say the one row by itself has more nodes than everything above it. But certainly if I add two rows together like that, those 2 rows together will always have more nodes than all the levels above them. So for any complete tree, you can say, well, I have at least half the nodes in these 2 levels. I'll have at least 3/4 of the nodes in the bottom 3 levels, and so on. So if on the average, I expect to be inserting something that, given all my numbers, if I was to order them from low to high, I'm somewhere in the middle of that range of elements. Well, if I have 75% of my values in the bottom 3 rows, simply because of the structure of the tree, what are the chances that the value I'm inserting is so small that it's going to be in the top 25% of nodes and will have to percolate up further? Not too great. I shouldn't say not too great, but the expected situation is that we will expect to be, it's more likely will be in the bottom 75% of nodes than that we'd have to actually percolate up a few extra levels, and their value that we've inserted is so small that it has to be percolated up into the top 25% of values. And even if that happens, 7/8 of the values are going to be in the top 4 rows. So in other words, it becomes less and less likely we'll need to move up to the next level. And so in the average case, we only expect to have to move up 2 or 3 levels, and it's it's even less likely we need to move up further than that. So for every level we actually do move up, the idea of saying, oh, well, my value is so small, I'll need to swap with what's still above me, that becomes less likely. And we do expect that whenever we do an insertion, the expected situation is that it only moves up 1 or 2, maybe 3 rows, and then stops. And in very rare cases, it would go past that. Deletement, on the other hand, when you actually do you expect that the value you're swapping downward is going to have to go down to that chunk of 75%. So if you have a lot of your nodes in the bottom few levels, well, you expect that whatever you're percolating downwards, whatever you're swapping downwards, is going to end up in those bottom few levels as well. And so you say, well, that means that I'm going to have to swap all the way down the tree. So with insert, we expect we'll end up in the bottom few levels. Since we start in the bottom few levels, there's not much to do, and the average would be constant time. For remove, for deletement, we expect to end up in the bottom few levels, because that's where most of the nodes end up. And yet, we're starting at the top, and so we do have to percolate all the way down. And so delete min, even in the average case, will be log n. Because delete min will require percolating down the whole tree, even on average. Insert says, the worst case, you might percolate up the whole tree, but on the average, you only go a few levels up, because most of the nodes are on the first few levels. So the average for both is you settle where in the bottom few levels, and so the difference in running times in the average case is simply due to the fact that with insert, you start where you want to end up in the bottom few levels, and with delete min, you start at the top, so you have to go down to the bottom few levels. Like I said, all you really need to worry about is the worst case. My concern is there. The average case is a little more complicated, and so I want to sort of hand wave an explanation of why that would be, but it's not something I expect you to be able to explain, and you may be still a little vague on it yourself as to why it is even the case. So that's just for your information. The worst case is what you're expected to know. And that's about it. That's priority queues. The constant on those logarithms are very fast. So we had here, of course, let me actually throw that back. We, of course, have then that is empty and find min, we've mentioned, are both constant time. So is empty and find min are both constant time. Delete min is logarithmic. Insert is logarithmic. But those two logarithmic operations have very, very low constant. That, moving from the array doesn't use extra pointers. You use only enough memory to store your keys, or perhaps key info pairs, if you're doing things that way, where your key is your priority and your info is whatever process you want to run or whatever. And then and then you can move up and across the array from the quote-unquote parent to the quote-unquote children and back, just doing bit shifts of your array indices. So all this is going to work very fast with not many hidden constants. The TAs will show you some code in that respect. The other thing I want to mention, and the TAs might mention this too, just so you know, we'll sometimes talk of a min heap or a max heap. Our discussions so far have been min heap, where we say each node is less than its children. We could also have ordered it the other way and said we have a max heap where each node is greater than its children. And our discussion will work exactly the same way, except our partial ordering principle would involve making sure each node is greater instead of less. And the whole discussion today has been using min heaps, but you'll sometimes see the term min heap or max heap, and that's just referring to the idea that your partial ordered principle is arranged that the node is less than its children, or alternatively with a max heap, the partially ordering principle is arranged that each node is greater than its children. But the rules are all the same, it's just a matter of which comparison you use. So do you say I swap upwards as long as I'm less than my parent, or do you say I swap upwards as long as I'm greater than my parent? So if you want to use a max heap instead, you take everything we've talked about today and flip the less than to greater than and vice versa. And that's it. That's priority queues. That's the last lecture that the exam will deal with. And I will see you for disjoint sets in lecture 30. Take care.